In question 1, you're given this diagram of the complex plane with a point W, which is at -1 plus root 3I. And your first question is to write W in polar form. In other words, using the distance from W to the origin and the angle that W makes to the positive real axis. So what we need to find then, first of all, this distance R and this angle here, which we tend to call theta. We can't immediately though, so what we have to do is set up this triangle here, where this length here is root 3, the height of W from the real axis, and this length here being 1 as the distance from W to the imaginary axis. And since we know that the imaginary and the real axes are at right angles to each other, then we can also say that this here is a right angle. To have this right angled triangle set up, we can find R using Pythagoras' theorem. Secondly, we can't find this angle theta immediately either. So what instead we have to do is find a different angle, which we call alpha. And since alpha is part of this right angled triangle, we can easily find it using just the basic trigonometric identities.
Now we know that we need the length of the complex number and the angle it makes. Well, let's just get the length first. We can use Pythagoras' theorem for that because we know it's a right angled triangle and we know the length of two of those sides. Well, the adjacent side, let's call it, is -1 and the opposite side is root 3. So we can take the principal square root of -1 squared plus root 3 squared. That gets us the square root of 1 plus 3, which is the square root of 4, and that gets us 2. So the length of our complex number is just 2 units. Now to find the so-called reference angle that my complex number makes to the real axis, I'm going to use tan inverse of root 3 over 1. Remember, root 3 being the opposite side of our triangle and 1 being the length of the adjacent side. If I wanted to, I could use sine or cos here, because I have the length of the hypotenuse, so just work that out. You won't always end up with a nice round number like 2 for the length of the hypotenuse though, so generally you would use tan. So I take tan inverse of root 3 over 1 and I get pi over 3. So that's the angle that the complex number makes to the real axis. To find the theta that I need for my coordinate system then, I take pi being 180 degrees and take away my reference angle, which was pi over 3, and that gets me 2 pi over 3 radians. Lastly then, to find the coordinates of W in terms of polar coordinates, I can replace the x coordinate with r cos of theta, and I can replace the y coordinate with r sine of theta. So r being 2 then, and theta being 2 pi over 3, the x coordinate is 2 times cos 2 pi over 3, the y coordinate is 2 times sine 2 pi over 3. And don't forget your I there, that just indicates that it's the y coordinate. You can check your answers here as well just by working out what cos 2 pi over 3 is. But that's minus a half, multiply that by 2 and you get -1, which is the x coordinate you started with. You can take sine of 2 pi over 3, that's root 3 over 2, multiply that by 2 and you get root 3. And that's exactly what you started with again.
Part 2 asks us to use de Moivre's theorem to solve this equation, z squared is equal to -1 plus root 3i, giving your answer in rectangular form, i.e. in this form here, as opposed to using polar form. If you have keen eyesight, you may notice a similarity between these two equations. In fact, w and z squared are equal, and that's key to using de Moivre's theorem. We have w in polar form, so in fact we have z squared in polar form as well. And since we have z squared in polar form, that allows us to use de Moivre's theorem.
We worked out in the last part of the question that -1 plus root 3i is actually equal to 2 times cos 2 pi over 3 plus 2i times sine 2 pi over 3. Well, I can take the 2 out as being common and say that my z squared then is equal to 2 times cos 2 pi over 3 plus I sine 2 pi over 3. To get z on its own then, I have to take the square root of z squared. Naturally then I'm going to have to take the square root of the other side as well. Notice I'm not just taking the principal square root, so I'm going to get two answers here, the plus and minus answers. Well, when I take the square root of 2, I just get root 2, and I'm going to leave it like that for the rest of the question. We don't need to use decimals here. And with this cos 2 pi over 3 plus I sine 2 pi over 3 to the power of a half, and remember power of a half just means square root, I can apply de Moivre's theorem to that. De Moivre's theorem just states that I can take this power of a half and get rid of it there, multiply it by both of these angles. So that gets me plus or minus root 2 that I have from before. The cos 2 pi over 3 just becomes pi over 3 because I'm dividing by 2, so I get rid of this 2 here. Same thing happens with the I sine. I get rid of the 2 here, so I just get pi over 3. I can just apply trigonometry then to work out cos pi over 3 is a half, sine of pi over 3 is root 3 over 2, and I can just work away at my answer from there. Now I can just finish off that question by taking either the plus or minus root 2 and then multiplying it in. So if I take plus root 2, then I get root 2 divided by 2 plus root 3 times root 2 divided by 2. A lot of 2's there. Now remember, 2 is just root 2 times root 2, so I can cancel 1 on the top with 1 on the bottom, and I end up with 1 over root 2. Same thing here, this 2 is going to be root 2 by root 2. Cancel 1 on the top with 1 on the bottom, so I get root 3 over root 2, and I keep my I. The other scenario is if I take minus root 2 here instead and then multiply it in, so I get pretty much the same thing except there are minuses everywhere. I get the root 2 over 2, cancel one of the root 2's with 1 on the bottom, and same thing over here, and I get minus 1 over root 2 minus root 3 over root 2 times I. Those are your two solutions for z. If you want to check, you can multiply these two together and you should get minus 1 plus root 3i.
This is what you're given in part B then. This diagram here with 4 points. You're told that they are z1, z2, z3 and z4, and they're all complex numbers, which makes sense given that we have a real axis and an imaginary axis. You're also given these 3 bits of information here. z2 is equal to I times z1, z3 is equal to k times z1, where k is a real number, and z4 is equal to z2 plus z3. Let me just remind you of a few things then. Multiplying a complex number by I is equivalent to rotating it by 90 degrees. So for example, if I were to take some point there and multiply it by I, all I'm doing is moving it around to about there. Secondly, multiplying a complex number by a real number just changes how far away it is from the origin. So again, if I take this point here, multiply it by say 2, all I'm doing is I'm going to move that point about twice as far away from the origin. So it's about there, and all 3 of these points should be collinear. I know this doesn't really look linear, but ignore that. If I multiply it by a half or something, then I'm just taking it half away as far as the origin, so it would be about there. Lastly then, when I take the sum of 2 complex numbers, let's say I take this one that already exists and this first one, it's the same as just applying one and then the other. So let's say I'm adding this one and this one. First of all, I go from the origin to there. Then I go from the origin to here, except that my start point is actually in here now. So I go something like that. And it should be the same as if I started in the other direction. So if I go from here to here, and then apply this complex number, it should take me to about there again. How can I use that information then? Well, let's just start with this one, with the rotation by 90 degrees. First of all, you can immediately say that neither of these two is z1. Because if you take this and multiply it by I, you're moving it down there. If you take this one and multiply it by I, you're moving it down there. And there's no points down there. So neither of those can be z1, because there's no possible z2 down here. So that means that one of these 2 points must be z1, and then one of these 2 points has to be z2. Nextly, z3 is equal to k times z1. Well, we don't know what k is yet, but we do know it's a real number, so that means that z3, z1, and the origin are all collinear. So let me draw some lines. There's a line there, the line there, there's a line there. Well, in fact, this line goes through 2 different points. So that tells us immediately that these 2 points are z3 and z1. And we knew before that one of these 2 points was z1, so it makes sense that z3 is also going to be on this line. Lastly, we're told that z4 is equal to z2 plus z3. Well, we already know that z4 and z2 are these 2 points, because z1 and z3 are these 2. And since z3 is one of these 2, we know that when you apply z3 to another complex number, it moves up and to the right. So if we take, say, this number, and move up and to the right, we go up here and there's nothing there. If we take this complex number and go up and to the right, we get to the other point. So that means that this one must be z2. So let me just mark that. z2. Secondly, we also know that this is z4 now. And now you could pretty much say that this one must be z3 because it's the same distance between those two as it is from 0 to this point. You could also say that because z2 is I times z1, you could sort of work backwards. You could use a protractor or something and say go backwards 90 degrees and you get back to there. So you can use either of those and that'll tell you that that is z3 and that is z1. Part 2 asks you to write down the approximate value of k. So remember, k is the number that you multiply z1 by to get z3. Now because z3 is closer to the origin than z1, you know first of all that k is a fraction that's less than 1. And you could use a ruler or something, but you can pretty much say that just k is 1 over 2. Or well, really it's approximately 1 over 2. Even if you measure with a ruler or something, you still can't be absolutely positive that's a half. But yeah, that seems pretty likely.